So the scenario now we are going to be working with is that the population standard deviation, okay, the population standard deviation is known to us. So there are two assumptions for the z-test for a mean when your population standard deviation is known. First, your sample is random. Number two, the size of your sample is more than 30, or the population is normally distributed when your sample size is less than 30. Okay, so these are the two assumptions we make. Okay, the critical or rejection region, okay, is the range of z values that indicate that there is a significant difference between your population and the observed means. Observed means refers to the mean that you observed when you conducted the experiment, and that the null hypothesis should be rejected. Okay, that's what your rejection region is. The rejection region, for the most part, they tend to lie towards the extreme end of your normal distribution curve. Now you have one-tailed test and you have two-tailed test. A one-tailed test, okay, indicates that your null hypothesis they should be rejected when your z-test value, okay, is in the rejection region on one side of the mean. Okay, one side of the mean. It could be either right side of the mean, which would be called right tail test, or it could be on the left side of the mean, which would be called left tail test. So let's look at this example right here. This is an example which is a right tail test. Now here, my rejection region, it lies over here. And the rejection region you determine by finding critical value. Okay, this critical value is what actually determines the rejection region. And this is my rejection region. So if your z value lies over here in this part, okay, then you are going to reject your null hypothesis. Same thing with your left tail test. This is your critical value. This actually determines your boundary for your rejection region. All right, this one determines the boundary. Now, if your z value lies in this area, then you reject it. You reject your null hypothesis. Otherwise, you do not reject it. Then you have two-tailed test. In this case, the null hypothesis should be rejected, okay, when your test value is in either of the two rejection region. So in this case, in a two-tailed test, your rejection region is going to be on this side and also on this side. Okay, and these rejection region they are determined by these numbers right here. These numbers, they're called critical values. Now comes this question: how do you find these critical values? You see these critical values right there. How do you determine them? Okay, these numbers. How do you find these critical values? For the most part, your alpha would be given to be as these numbers. Okay, these are your common alpha. Using this alpha, and depending on what type of test you're performing, you can find your critical value using z table. Okay, so I have entered few values of critical value by looking at the z table. These are the common ones. Okay, so my common significance values can be these are the common significance value which can be 0.10, 0.05, 0.01. So let's look at this one right here. If my alpha is equal to 0.10 and if it's a two-tailed test, then your critical value, because it's a two-tailed test, your critical value is going to be plus minus 1.645. So this is going to be my critical value right here. This is going to be minus 1.645, and this one is going to be plus 1.645. Okay, and my rejection region would be this right here. Okay, this would be my rejection region. Now, on the other hand, if if your oops, hold on, if it's alpha is 0.1, okay, and if it's a one-tailed test, and if it's specifically right-tailed, okay, it's a one-tailed or one right-tailed test, in that case, you're going to use critical value is going to be plus 1.28. It's going to be plus 1.28. So it's if it's a right-tailed test, this value, okay, is going to be plus 1.28 if your alpha is equal to 0.10. All right. On the other hand, if alpha equal to 0.10 and if it's a left tail test. Okay, if it's a left tail test, your alpha, your critical value is going to be minus 1.28. So in this case, this value, okay, this value right here is going to be minus 1.28. Okay, now on the other hand, if, okay, we're done with this, we're done with this. Now let's say your alpha equal to 0.05, and if it's a two-tail test, if it's a two-tail test, then your critical value is going to be plus minus 1.96. So this is going to become minus 1.96, and this is going to become plus 1.96. Okay, when your alpha is equal to 0.05. On the other hand, when your alpha is equal to plus 0.05, and if it's a one tail test, let's say if it's a right tail test, okay, if it's a right tail test, your alpha is your critical value is going to become plus 1.645. Okay, it's going to become plus 1.645. So for right tail test, which is this one right here, this value is going to become plus 1.645. On the other hand, if it's a left tail test, all right, at alpha equal to 0.05, this is going to become minus 1.645. So this value, this one right here, it's going to be minus 1.645. Okay, assuming now you understand this, let's try to apply this in our hypothesis testing problems. So these are the steps we follow when we solve hypothesis testing problem. Number one, make sure your preliminaries are satisfied. So make sure that the two assumptions that for the z-test value for a mean when sigma is known are satisfied. Number one, that your sample is random. Number two, that your number of sample size is more than 30, or the population is normally distributed when your n is less than 30. So make sure these two conditions are satisfied. Step one, state your hypothesis and identify the claim. That's the step one you do. Step two, okay, step two, you find your critical values from the z table using the significance level. Okay, so this you can, for the most part, your alpha is going to be these values. So for the convenience, I have put these critical value right here. These are my critical values. Okay, you can actually look it up on this table and determine which is my which critical value I'm going to be using. Okay, then step three, you compute your z value, also known as test value. So the way you compute using this formula right here. Okay, here your sample mean. Okay, your x bar is gonna be sample mean. Okay, this is your sample mean. Your mu is gonna be your population mean. All right, your sigma is gonna be your population standard deviation, and n is gonna be your sample size. Now, be aware your x bar is the sample mean. All right, and this one right here, mu, is the hypothesized population mean. Step 4. Now you make the decision to reject or not reject the null hypothesis. If you're doing right tail test, okay, in that case, if your z value is more than critical value, then you reject the null hypothesis. On the other hand, if you're doing left tail test, okay, which would be right here. If you're doing left tail test, which is right here, if your z value is less than the critical value, in other words, your z value falls in this range, okay, it falls over here, then you reject your null hypothesis. You reject your null hypothesis. Same thing with your right tail test, okay, right tail test right here. So if your z value for the right tail test, if z value falls in this region, okay, if z value is greater than critical value, okay, then you reject the null hypothesis. Then comes your two tail test. If your z value falls in the reject region, okay, let's say your z value falls over here, somewhere over here, or maybe it falls over here. If it falls over here, then you're gonna reject your null hypothesis. This is a rejection region. Okay, these are rejection region for a two-tailed. For left tail, this is my rejection region. For my right tail, this is my rejection region right here. All right, and then at the end, you summarize your result. Now let's look at some examples. Let's look at the example of a right tailed first. So let's say In a population of metal components, okay, the average lifetime without any protective paint coating, okay, if you do not put any protective paint coating on a metal, then the average lifetime of that metal is going to be 101 month. The lifetime is normally distributed. Okay, let's say this is given to us, and also we know that the population standard deviation is 15 months. Again, this information is provided to us. Now, an engineer, okay, he claims that when he applies or when he or she applies the new protective paint coating, it increases the mean lifetime. Okay, it increases the mean lifetime of the component of the metal component beyond 101 month, meaning the lifetime actually increases. That's what she claims. So she tests this claim. Okay, and what she does, she selects a random sample of 50 components with the coating, and these are the values she finds. These are the values. These values indicate the time, okay, for how long the metal lasted. For example, this one right here, this indicates that the metal lasted 114 days. This one lasted 107 days. This one lasted 115 days, and so on and so forth. So all of these, they had coating applied to them. Now test the engineer claim at a significance level alpha equal to 0.05, or you can say at 5%. Answer. First, you want to make sure that these preliminaries are satisfied. Well, we know our sample is random, right? Number two, we know our sample size is more than 30. It is 50 as a matter of fact. You can come and you can check. It tells you there are 50 sample values. All right. So that preliminary is satisfied. Now we can proceed. Step one. All right. Step one was state the hypothesis, identify the claim. My hypothesis would be a null hypothesis would be that the mean lifetime is 101 month. Okay, the coating has no effect. It did not help at all. That's my null hypothesis. My alternate hypothesis would be that the coating did increase the mean lifetime. And this would be, by the way, a right tail test because this is greater than, okay, a mean is greater than 101 month. All right, then step one is done. Now, step two, you find your critical values. Well, my alpha is 0.05 and I know it's a right tail test. So come back and look at this table. Alpha equal to 0.05. Okay, and it's a right tail test. So it's going to fall in this category. Okay, right tail test. So my critical value is going to be plus 1.645. Plus 1.645. Come over here and you can see my z value, okay, my critical value is going to be plus 1.645. I'm just rounding it off and I'm writing it plus 1.65. Now this value is this one right here. Okay, so this value is my plus 1.65. So if my z value, okay, this is my critical value right here, this is my critical value. So if anytime my z value falls over here in this range, we are going to reject null hypothesis. Okay, so let's compute our z value, our z test value. This is the formula I'm using. All right, your x bar is your sample mean, and this is your population mean. I substitute my sample mean, I put my population mean, and I divide my standard deviation, and also divide standard deviation by root of sample size. And my answer comes out to be 2.82. 107 is right here. Okay, and how I did came out 107. Basically, I took the sample mean of above samples. I took all these numbers, okay, add them all together. Okay, all these numbers, add them all together, and you divide by 50, and the answer would be 107. Okay, all right. So my z is 2.82. Step 4. Now you're going to make the decision to reject or not reject the null hypothesis. So the decision we do is like this. If it's a right tailed, okay, well, in this case, it is a right tailed. So if your z value is greater than critical value, then you're going to reject the null hypothesis. Well, come down over here, and if you look at your z value, this is my z value, okay, and your z value is over here. It is falling in this area, okay, plus 2.82. So my z value is greater than 1.65. So reject the null hypothesis because it falls in the rejection region. Step 5 now. Now you make your conclusion, summarize your result. So at the 5% significance level, there is enough evidence to support the claim that the paint coating does increase the mean lifetime of the component. That is your summary right here. Okay. So in this case, we are rejecting the null hypothesis and we are going for the alternate hypothesis. Example 2, left tail test. So let's say a water treatment plant, okay, they claim that they have a new filtration system. And this new filtration system, it will reduce the contaminant level to below 5 parts per million, which is the population mean. Okay, we know the population mean is 5 ppm. The environmental engineers, they want to verify that the system performs better than this standard. So what they do, they take a random sample of 60 water samples, all right, and then they test. And actually, they take a sample and then they make some measurement, and the measurement shows that the mean contaminant level is 4.9 parts per million. And then they also know that the population standard deviation is 0.8 ppm. So they know these things. Now, test the claim that the filtration decreases the contaminant level at a significant contaminant levels at significance level of alpha equal to 0.05. All right. Step one. Well, before you do the step one, make sure your preliminaries are satisfied. All right. That this condition right here, this condition is satisfied, and as you can see, the sample is more than 30, so it is satisfied. Okay, and these are normally distributed data. State your hypothesis and identify your claim. My hypothesis is that my mean is 5 millimeter, 5 ppm. Okay, there's no improvement. Not ppm, it should be ppm. Okay, and your mean is less than 5. That will be my alternate hypothesis. So in this case, my claim would be that the system reduces my mean contaminant level. So this is left tail test. All right, step 2. Now you find your critical values. Here we're going to look up in the table. My alpha is 0.10 and my test is left tail test. So because my alpha is 0.10 and it's a left tail test, if you come over here, 0.10 is right there. All right, and it's a left tail, right? So left tail right there is minus. So the answer would be minus 1.28. So my critical value is going to be minus 1.28. So this value is my critical value, minus 1.28. So this is my critical value right there. Okay, now you compare z value, okay, a z test value. I use my formulas, okay, this is my sample mean, this is my population mean. Okay, my sample mean is 4.9, it's given to you right there, okay, and then my population mean is 5, okay, population mean is 5, that's given to you right here. Okay, substitute the formulas and your z value comes out to be minus 0.968. So this one is minus. So 0.968 will fall somewhere over here. Okay, minus 0.968. So since minus 0.968 did not fall in this rejection region, it did not fall over here, right? It did not come over here. It falls in this area. So we are not going to reject null hypothesis. Okay, so do not reject null hypothesis. So do not reject null hypothesis. Now you summarize your result that at the 5% significance level, okay, there is not enough evidence to conclude that the new filtration system reduces the mean contaminant level below 5 ppm. That is your summarization, or that's your conclusion. Now let's look at this example, which is a two-tailed test. A medical researcher is interested in finding out whether some new medication will have any undesirable side effects. Okay, and they're specifically testing on patients' pulse rate, whether it's going to increase, decrease, or the pulse rate. So the researcher is particularly concerned. He's worried whether the pulse rate is going to increase, or maybe decrease, or maybe it stays the same after taking the medication. So the researcher, he knows that the mean pulse rate for the population, he knows that for the population is 82 beats per minute, 80 bpm. Okay, and that the population standard deviation is 5 bpm. He already knows this information. So to investigate, okay, what the researcher does, he selects a random sample of 60 patients. Okay, he selects a random sample of 60 patients who take the medication, and then he finds that their mean pulse rate is 80.7 bpm. So test the claim that the medication does affect the mean pulse rate at a significance level of this alpha equal to 0.01. In other words, at 1%. Answer. First, you state your hypothesis and identify your claim. In this case, my null hypothesis and alternative hypothesis are this, that the medication has no effect on BPM. That's my null hypothesis. My alternative hypothesis is that the medication does affect the BPM. Maybe it goes up, maybe it goes down. Okay, it does affect it. So this would be a two-tailed test. Okay, because I'm saying my mu is not equal to 82 beats per minute. Step two, you find your critical value. I know my alpha 0.01, and I know that the test is a two-tailed test. So going back to this table, okay, looking at alpha equal to 0.01, which is right here, okay, and it's a two-tailed test right here. So my critical values are going to be plus minus 2.576. So my critical value is these numbers right here. Okay, I just rounded them off. So this one is this value. Okay, this is minus 2.58, and this one is my other one, which is this right here. Okay, so this is going to become minus 2.58, and this is plus 2.58. Now you compute your z-test value. Well, this is the formula I use. Okay, I put my sample mean, I put my population mean, and I put my standard deviation, and I put my sample size. And my answer comes out to be minus 2.0137. So minus 2.0137. This will be somewhere in this area. So now we make the decision. Step 4, make the decision to reject or not reject the null hypothesis. Here, minus 2.58, right? The critical value is smaller than minus 2.0137. So do not reject the null hypothesis. You see, this value, it falls in the do not reject area or do not reject region. So do not reject your null hypothesis. Now you summarize your result. At the 1% conclusion, at the 1% significance level, there is not enough evidence to conclude, okay, to conclude that the medication has any effect on mean pulse rate.